This tutorial consists of 16 slides which will go through and explain the information that's also available in a chapter of an accompanying textbook. And it's all about understanding the rocket equation, which is related to understanding how rockets actually get to space. So we're going to start with a fundamental question which we will verbalize first, and then we will start looking at it from a mathematical and visual standpoint. The question is, why are rocket engines so inefficient in burning fuel to get a rocket into space? And a couple of years ago, a student of mine had a very good description of this, so I've been using it ever since. The main reason you cannot convert 100% of the energy of kerosene into kinetic energy is because the fuel has significant mass and that the fuel is burned continuously instead of instantaneously. As a result, when you burn 1 kilogram of fuel to lift 1 kilogram of payload, you also need to accelerate the mass of the fuel as well. So when you light the engines of this rocket, you are actually accelerating all of the mass at liftoff. This additional mass increases the inertia and reduces the effective delta V, change in velocity, of your rocket. So you need to add more fuel to reach the desired 7.8 kilometers per second of change in velocity needed. Overall, this produces a delta V function that is logarithmic. So this is a complex engineering topic, and in order to learn complex engineering topics, my recommendations are pace yourself. Go through things in small steps, and also find multiple sources. In order to produce this particular tutorial and for me to understand it and explain it as thoroughly and clearly as possible, I actually used all 3 of these textbooks. The other thing that can help you understand complex engineering topics is to find something that's analogous and visualize it. So in previous years in class, I would bring balloons. Students would inflate the balloons, and when you release these balloons, they fly around in the air exactly the same in which way that a rocket flies in the air, except a rocket obviously is much more controlled. Okay, so let's get into the topic. And we're going to be looking at diagrams. Here's an example of a diagram that we'll be seeing. And there are a set of equations that are useful to understand as well. One of those has to do with potential energy, mass times change in height times the acceleration of gravity. Another one has to do with momentum, and which is mass times velocity. And I want to help you understand that momentum, if you look at momentum and changes of momentum, the integral of the change of momentum over the change in velocity, or multiplied by the change in velocity, is how we actually get to kinetic energy. So in this tutorial, I'm going to use integrals. I'm going to use some concepts from calculus. Not all of you may have seen that, but I think you'll appreciate that calculus is important. And this is a good opportunity so that when you do see calculus, you'll say, wow, great, now I can solve these problems as well. So that's one integral we have to understand. The other integral that we have to understand is that the integral of dx over x is the natural log of x. Okay, so let's get started and make sure that we understand some other things. So this is the second diagram that we will be using, and I'll explain it more later as we go on, but there are some fundamental things, values that we've been looking at that we also need to understand. Orbital velocity of the Earth at the International Space Station, which is 400 kilometers up, requires that you're traveling at a velocity of 7.8 kilometers per second so that you don't fall back to the Earth. At 25 degrees north latitude, which is where Florida is located, the Earth's surface moves eastward at a velocity of 0.4 kilometers per second. So by launching rockets to the east, we only need a delta, a change in velocity, of 7.8 minus 0.4, or 7.4 kilometers per second. As a quick aside, the most efficient place to launch satellites is at the equator, because the Earth's surface moves even faster than this, and that's why the French have their launch site in French Guiana, which is on the northern part of South America, very close to the equator. For reference, also, the speed of sound is 0.34 kilometers per second. So from that, you can see that orbital velocity is more than 20 times the speed of sound. And the equation for kinetic energy is 1/2 mv squared. And this is the kind of energy that is the primary energy that something will have when it orbits. Okay, so there's a textbook, and there's a link to that textbook, which I've given you also. And in that textbook, it goes through step by step and explains things as well through a series of equations. In particular, this set of equations shown here are the most important ones to understand, and they're in sections 11.2, 11.3, 11.4, and 11.5 of this particular chapter. And on the right, you can see the specific equation numbers we're going to be working with. So you'll see these again. So I'm going to continue to flip, and then you'll see how it works. So we also, as we know in our 7-step problem-solving process, we have to really understand the diagrams that are related. And the typical diagram that you would use for statics or dynamics is called a free body diagram, which is a picture of the directions and magnitudes of forces on an object. In this particular case, the textbook chapter uses this particular diagram, which we will further simplify, but it has all of the variables on there and shows how those variables relate. Let's also define what we mean by mechanics, what we mean by statics, and what we mean by dynamics. So these are courses that mechanical engineers and civil engineers will take. Mechanics is the study of forces, and so that's very similar to the first semester physics class that you take. Statics is the study of forces on stationary objects, i.e. where the sum of the forces equals 0. And dynamics is the study of forces on moving objects, where the sum of the forces equals the sum of the masses times accelerations. In this case, we have a dynamics problem, and let's set that problem up. So you've seen these two diagrams already, but we're going to be looking a lot more at the diagram on the left, and we'll also be talking a lot more about the relevant theory. So let's get started with that theory. Dynamics says the sum of the forces equals mass times acceleration. The forces that are on a rocket is the thrust, which is causing it to accelerate, the drag caused by air friction, which would cause it to decelerate, and gravity, which would cause the rocket to fall back to the ground. Now, to simplify the equations, we already know that kinetic energy is more important than potential energy, so we're going to ignore the drag forces, and we're also going to ignore gravity. And in the diagram that you see on the right, there's a curved trajectory, which means that there's some other things going on. We're going to assume that we have a straight trajectory also. So what matters is the thrust equations. So thrust equals mass times acceleration. We're going to be working with that particular equation. So let's understand thrust. Thrust relates to the concept that explains how can an object ejected from a vehicle going in one direction gain velocity in the other direction if there is no gravity, so if there's nothing to push against. Well, the way it works is the concept of conservation of momentum. And the conservation of momentum says that the mass times the velocities must stay constant. So if we have two masses that are together moving at the same velocity, and we separate those so that V2 is different from V3, this is the basic concept of how a rocket engine works. But let's make this a little more visual. So when we start out, we have two masses. They are attached to each other, and they're moving at one velocity. At another point, the two masses are moving at a different velocity. And the way a rocket works is that mass 2 is being pushed out the back of mass 1. And that causes V2 to be greater than V1 and V3 to be less than V1. And it is this fundamental that is shown in this diagram. But now what we're going to do is, instead of showing it as a block and having this only occur once, we're going to have this occur continuously. So that's what this diagram shows. So there is a continuous ejection of mass out the back of the rocket engine. And then what we have is we have an equation for thrust, which is defined as by the letter T, is the change of mass over time that is getting ejected, which is this m dot, multiplied by the difference in velocity between the two items. So the difference between V2 and V3 in the yellow boxes above, and that is, we're going to define that as V plus delta V times a direction, which is VE that you see there. Okay, so we're going to continuously eject out the back, which causes the rocket that you see to accelerate between time t and time t plus delta t because of the mass that is moved back. So that equation, T equals C times the rate of change of the mass, m dot, is important. So we're going to look at that equation again, and we're going to define another variable, which is basically the definition of how rockets work and the key characteristic to make the best rockets possible. And that's something called specific impulse. Specific impulse is defined as thrust divided by the rate at which the mass of the rate at which the weight, which is mass times the acceleration of gravity, of the propellant is being expelled from the rocket. So let's start with the equation that we saw before. Thrust equals the rate that mass is going out the back at times, which is m dot, times the velocity that is going out the back. Now we have our definition of specific impulse. T minus the change of mass multiplied by the acceleration of gravity, which is kind of actually really the change of weight, if you will, the way it would get measured on Earth. And we're using gravity at zero sea level. And so, with those two equations, we can also define C as therefore being the specific gravity multiplied by the specific impulse multiplied by gravity at sea level. Okay, so that C, think of that as this exhaust velocity. If we have a high specific impulse, it means that we are using propellant efficiently, and it also means that we have a high exhaust velocity, or difference in the velocity of the rocket and the velocity of the mass when it leaves. So for rockets lifting off, we need not just a high specific impulse, but we also need high thrust, because if the thrust isn't big enough to counter gravity, then the rocket can't go anywhere. So the primary engines that are used are either solid fuel rockets or liquid fuel rockets. Those have, for the technologies that are available currently, typically have an ISP, the specific impulse, of around 250 seconds or 300 seconds. Funny units for ISP, but that's the way it comes out if you actually look at the units. If you multiply the specific impulse by gravity, you will get this exhaust velocity in meters per second, and that's typically between 2,500 meters per second and 3,000 meters per second, which could also be said as 2.5 kilometers per second or 3 kilometers per second. So as you can see, that is less than the velocity that you need for orbit. And these types of rockets have massive amounts of thrust, which can be measured in meganewtons, where there's an alternate technology which would be much more efficient, and that's an ion thruster. And you may have heard about those in various different kinds of movies. So it's about 10 times more efficient in the way in which it uses fuel, because it exhausts the fuel at much, much higher velocities. But currently, we haven't been able to make them with having any really significant amounts of thrust. So where liquid rockets are measured in meganewtons, ion thrusters are measured in millinewtons. So they are 10 to the 9th times less powerful, if you will. And so they are efficient but not powerful, which is why we can't use them to take off from the Earth. But they are used on things that are in space. So when we have a spacecraft that's already left Earth, we can use this to send it to various different places. It just takes a long time for it to accelerate. Okay, that's a bit of a digression. Let's go back to our 7-step problem-solving process. This is where we last left our equations. We now have some equations to add, which are these equations related to specific power and specific impulse, and you can see those equations there, and we'll be using them more because now we can derive what is known as the rocket equation. The rocket equation was first derived by a Russian mathematician more than 100 years ago, and it explains this concept of the fuel accelerating and what the equations actually end up looking like. So thrust equals mass times acceleration. The thrust is also defined as the exhaust velocity times the change in mass divided by change in time. And so we have two equations for thrust. We can combine those. We have mass times acceleration equals the exhaust velocity times the change in mass over change in time. Acceleration can be defined as the change in velocity over change in time. So we do that substitution. We have mass times the change in velocity over time equals the exhaust velocity times the change in mass over time. We can then get rid of the dt's that are underneath. We can move the mass, all the mass information to the right side by dividing by mass, and we get the equation. The change in velocity equals the exhaust velocity times the change in mass over the current mass. So this we can now integrate. If we take the integral of the change in velocity and we take this constant, which is the rate of the exhaust velocity times the change in mass over the instantaneous mass, we can then do that integral, and we get the final velocity over the initial velocity equals the rate at which the exhaust velocity, which the mass is moving out, times the natural log of the initial mass divided by the final mass. So now we have something that we can work with, and we have this natural log relationship. So we can redefine some things. So the final velocity over the initial velocity, we'll just call that delta V. We will substitute in for this C as being the specific impulse times the acceleration due to gravity, and we have the equation that you see there. And that equation is the one that ends up getting used. So if we remember our verbal description of this, I've posted it here again, and I won't reread it, but you may want to stop, look at it. It basically describes the math that we have just done. So now we're going to go back to our 7-step problem. We are going to include the math that we have just done, which is the equation that you see here. So the change in velocity, and remember, we're ignoring drag, we're ignoring gravity in order to do this, and we end up with that equation. So then what we're really trying to go to is, why do rockets have to have more than one stage to lift off from the Earth? So in order to understand that, let's go do a little bit more work, detailed work on various equations. A rocket, when it is sitting on the launch pad, consists of 3 different kinds of mass. The empty mass of the structure, the mass of the propellant and the mass of the payload. The payload is actually what's going to go into orbit. You have to have the structure in order to hold the propellant and the engines and everything. And so we can define that initial mass based on that equation. And when we finally have the mass when all the fuel is burned, then we have this MF, which is the empty mass plus the payload. So we have those two particular equations, and now we can define some ratios. One of those ratios is what we'll call the payload ratio, which is the amount of payload divided by the initial mass minus the amount of payload. So how much stuff do we have to throw away to get the payload up? The other one is what we'll call the structure ratio. So how much of everything other than the payload is the empty mass. So we have the total minus the payload, and then we have this empty mass. So ideally, you would want the payload to be big, and you would want the structure, you would want this epsilon, this second one, to be as small as possible. If we substitute those into the equation that we had previously, where we have M0 and MF now substituted, and we go and take those particular ratios, we end up with the equation that you see here. So the natural log of 1 plus the payload ratio divided by the structure ratio plus the payload ratio. Now let's look at some typical limitations that we have based on how we build these structures. We want to make sure we have a significant payload that is going into orbit. So typically the payload is somewhere around 1/20th of the takeoff weight. And when you go back and you see what we're going to cover, what we covered in class, you'll see that that's roughly right for the Soyuz and the Falcon rocket. The typical structure is about 10% of the rocket weight. So if we could make that lighter, the system would be better, but that's a pretty reasonable number to be working with. So if we plug those numbers into this 1 plus lambda over epsilon plus lambda, we will get the equation that you see here. We've got to take the natural log of that, and you end up with 0.19. So the amount of velocity that we can increase in a particular stage of a rocket is 0.19 times the specific power. As you saw in some previous slides, the specific impulse we have is typically around 300 seconds. We take the 300 times 0.19, and a one-stage rocket will only get us to 5.7 kilometers per second. When we get to 5.7 kilometers per second, we got to throw away a lot more weight, which is typically a whole bunch of the structure, which is why rockets are built with multiple stages. So we're getting a bit ahead of ourselves. There is the equation. There are the assumptions that we have used in terms of this structure ratio and payload ratio and the specific impulse. When we substitute all of that in, we get that delta V of 5.7 kilometers per second. We need 7.8 for low Earth orbit. That goes down to 7.4 if we launch from a place that is closer to the equator, like in Florida. But 5.7 is not enough, so we need at least 2 stages or some technical improvements to the rocket in order to make it work. Okay, so that's a lot of complexity, but it hopefully has taught you some things, and it demonstrates a bunch of things. How to learn complex engineering topics, free body diagrams, applying the 7-step problem-solving method, the use of calculus and physics in engineering, and a classic example of use of a logarithmic function. And now you have a better idea of the kinds of things that have to be optimized in the design of a rocket in order for it to go into orbit. I hope you've enjoyed this tutorial, and happy trails.